This is lecture 21 of the course on high performance computing. In lecture 20, we had looked at some of the problems and solutions to those problems relating to concurrent programming. We saw how locks, which are known as spin locks or busy wait locks, can be used to enforce something called mutual exclusion, through which shared variables between processes can be safely used. We also saw how something called the semaphore can be used to synchronize processes, to coordinate the progress of processes in order to achieve their common objective in a concurrent program. Just to remind you about an example that we saw relating to semaphores, the example that we had looked at had a situation where there were three processes, process P1, P2 and P3, which were cooperating towards the reading in multiplication and outputting of a matrix multiplication. And we saw how a semaphore could be used to, two semaphores could be used to synchronize the work as divided among the three processes. For example, process P1, which is reading the matrices, process P2, which is multiplying them, and process P3, which is writing the result. It could be set up so that a semaphore initialized to 0 could be used to block process P2 until process P1 had finished the reading, and another semaphore which had been initialized to 0 could be used to block process P3 from writing the result until process P2 had successfully multiplied the matrices. So with a little bit of thought, one could use semaphores for different kinds of synchronization of processes which are cooperating towards a common objective. Okay, now moving right ahead with some of the problems relating to concurrent programming. I had talked about potential problems that could arise due to the vagaries of shared variables, and we saw that if one just wrote concurrent programs using shared variables and did not identify and suitably protect the critical sections of the program, then the results could be somewhat unpredictable. The program may not do what you thought it was going to do. That's where the mutual exclusion problem and the need to identify critical sections came up. Now another problem which could arise in concurrent programs is a problem known as deadlock, and as the name suggests, it's a somewhat serious problem. Now to understand deadlock, let me just give you a very simple example of a deadlock situation. Let's suppose that I have a process which I'm referring to as P1. I'm just showing you a small part of the activity of that process. You notice that it starts by acquiring a lock, the lock called L, and the next thing that it does is to acquire the lock again. Now it's not too clear what this process was written to achieve, but if we think about this a little bit, we realize from our understanding of the implementation of acquire lock that let's suppose that process P1 is lucky in its first call to acquire lock. Let's suppose that the lock is currently available. Then what will happen is the net effect of acquire lock, if it is implemented using, let's say, test and set of L, is going to be that the process is going to test and set L so that the old value of L, which would have been 0, will get changed to 1. And the process will then proceed to its next statement, which is acquiring lock L again. And we know that since the lock L is currently held, in fact, by process P1, the second call to acquire lock is just going to keep on executing while test and set of L forever, because we know that this is not a situation in which the value of L is going to get changed, because the only possibility for the value of L to get changed is where this very same process executes release lock. And this process, every time it executes, is just going to keep on executing acquire lock, busy waiting on this loop inside the acquire lock function. Now this is in itself is not a dangerous situation, because we know that acquire lock involves busy waiting, and after the process has used the CPU for some amount of time, it could be preempted and will yield the CPU. But there could be a more serious situation if the acquire lock function is not written using busy waiting, but is using the blocking idea which I had talked about last time. And let's suppose that there's a situation where this is a blocking scenario. Then as far as process P1 is concerned, process P1 is in a situation where it is holding a lock and subsequently is trying to acquire the lock, but will be blocked until the lock becomes available. And the only process which can release the lock is process P1. And we know that it is never going to release the lock because it is currently blocked waiting for the lock to become available. And therefore this is a situation which will never happen. we know that this will never happen. And this has happened because of an incorrect use of the lock. When we first looked at this piece of code, I suggested that it's not clear what the programmer has in mind, because it's not easy to understand how a single process could try to acquire a lock, and while holding the lock try to acquire the lock again. It does not make any sense. It's not logical. Therefore, this is very clearly a wrong piece of code. But this is just a simple illustration of a more general problem which could arise if there are multiple processes. And this situation is known as a deadlock. And the situation could arise if there are multiple processes, each of which is trying to acquire a resource, maybe using a semaphore, and that resource is held by another one of the processes in such a way that there is a cycle of processes, each of which is waiting for something to happen that can only be achieved by the next in line in that cycle of processes. This ends up in what is known as a deadly embrace, where there is a group of processes which are in a sense blocked and locked, waiting for something that only one of the others in the group can do, which in turn is waiting for something that one of the others in the group can do, guaranteeing that none of these processes can progress ever. So this is much more dangerous than an infinite loop, because it is a guarantee that the processes are not going to make any progress. Now, deadlocks are a serious problem that could arise in writing concurrent programs, and they are serious in that unless the deadlock is understood and eliminated, the program is not going to achieve its objective. And we will talk about deadlocks again a little later. I wanted to introduce the idea, since we are talking about potential problems that one needs to be aware of in concurrent programming. Now, just to tie in the concepts of concurrent programming, it is often a teaching technique that is used in concurrent programming classes to look at some standard problems and analyze how they could be solved using the constructs of concurrent programming. These are known as some of the classical problems of concurrent programming. One of these is known as the producer's-consumer's problem. I thought I would run through this. It's also sometimes known as the bounded buffer problem. Now, the nature of the problem is the following. The situation is one where I have one or more processes which are producing. I refer to them as the producer process. So the property of the producer process is that it produces something and then puts it, the thing that has been produced, into a fixed size array or buffer. So when I use the word buffer, I am referring to something which we will represent as an array in the program. The property of the array is that it is a shared array and that it is of some fixed size. Now, the other entities in this concurrent program, or the other entity in this concurrent program, is what I will refer to as a consumer. And as the name suggests, what a consumer process does is it takes something out of the shared buffer, that's why it's called a consumer, and it uses that, whatever that thing was. Now, the problem that could arise is that if I write a concurrent program to handle consumer-producer-like situations as two processes, one is the producer process, one is the consumer process, and I just think about the code of the consumer process, the code of the consumer process is going to try to read something out of a shared buffer or a shared array and use that thing. But unless the producer process has already produced something and put it into the buffer, there may be nothing in the consumer process for the consumer process to consume. Similarly, if the consumer process, if the producer process has something which it has made and would like to push it into the buffer, but up to now the consumer process has not removed anything from the buffer and the buffer is therefore full, then the producer process may not just be able to insert the newly created thing into the shared buffer. Hence, there is a need to synchronize the activities of the producer and the consumer to make sure, for example, that the producer does not put into a full buffer or the consumer does not take out of an empty buffer. And these are what may be viewed as synchronization requirements between the producer process and the consumer process. So therefore, in some sense, it's a useful example to try to write code for in terms of a concurrent programming exercise. Right now, the other aspect which is interesting here is that the producer and the consumer not only have to be synchronized, but they also have shared variables which they are both accessing. Specifically, the shared variable that they have is the shared buffer. And therefore, we have to understand that in writing the producer-consumer concurrent program, we have to treat accesses to the buffer as a critical section. And therefore, there is, in addition to the synchronization requirements, there is a mutual exclusion requirement. Therefore, this is a nice problem to understand these concepts more fully. Let's just look at a possible encoding of the problem. So I described the shared buffer by this is not exactly C code, it's not exactly any program, but a programming language, but will be adequate for our purposes, the pseudocode form. So I have a shared buffer, an array which I'll describe as buffer. It is of fixed size. The size of this particular buffer is n. So I number the elements from 0 through n minus 1. And I have a producer process which is going to execute a loop in which it repeatedly produces a thing which I'll call x, and then inserts that thing into the buffer. So associated with the buffer I have an index variable called I, which will let me know the current available slot in the buffer. So I will initialize I to 0, and then subsequently whenever something is put into the buffer, increment I, which is why there is an I++ associated with the producer. And the producer does this repeatedly. What does the consumer do? The consumer once again repeatedly removes something from the buffer. In order to do that, it decrements I and looks at the object inside that element of the buffer or array, puts that into a local variable called y, and consumes y. Right? So this is the basic activity which we had talked about. Now there is a need to enforce the mutual exclusion requirement on the accessees to the shared variables. There is also a need to enforce the synchronization requirements of not making sure that the producer and the consumer do not produce and consume from empty or full buffers, etc. Okay, now one of the requirements that we have is that when the producer produces an object x, it must obviously check to see if the buffer is full. And if the buffer is full, then it has to wait for at least one consumption of an object to happen. And that will ensure that one element in the buffer is available, and that therefore the producer can push the x that it has produced into the buffer, can insert the x that it has produced into the buffer. So that is one of our requirements. The other requirement is that prior to thinking that it can take something out of the buffer, the consumer will have to check if the buffer is empty. And if the buffer is empty, it will have to wait. In other words, it cannot just proceed after the if condition. It will have to wait until at least one element has been produced. So it has to wait for at least one production. Okay, now we notice that there is the waiting for consumption and there's a waiting for a production. Now think about the consumption. When does something get consumed? Something gets consumed when it is taken out of the buffer by the consumer. When does something get produced? It gets produced when it is put into the buffer by the producer. And therefore we can think of these requirements as being synchronization requirements between the processors, between the processes producer and consumer, which could conceivably be handled using semaphores. Now another problem which people often talk about as a concurrent programming problem is what is called the dining philosophers problem. It's a rather curious problem. The problem is stated as follows. Let's suppose there is a circular table and there are n philosophers, n people sitting around the table. Each has a plate of food in front of him or her, and there is a fork on the table between each two philosophers. So the setting is as over here. There are n philosophers. In this example, n is equal to 5, and a plate in front of each with food on it. Unfortunately, there are not enough forks. We assume that each philosopher needs 2 forks to eat with. That's the suggestion. But there are only n forks on the table, which means that forks are a shared resource which is scarce. Now, they are called philosophers because all that the philosophers do is repeatedly, in other words, this is a loop, they think and then they eat. And in order to eat, they have to acquire 2 forks, because to eat, they have to get the fork on their left and the fork on their right and then eat. And after having eaten, they put the forks back and think. Now the problem that one has to deal with here is that it is possible that one could end up with some kind of a deadlock situation. For example, if this philosopher grabs this fork, and this philosopher grabs this fork, and this philosopher grabs this fork, and so on, there could be a situation where each philosopher has 1 fork, and therefore all of the philosopher processes will be deadlocked, unable to eat, because they cannot get 2 forks. Therefore, there is actually a serious need to make sure that these philosophers, or the code which is used to describe the activity of any one of these philosophers, is carefully written to ensure that this deadlock does not arise, where each philosopher ends up with 1 fork. So the problem is basically one of avoiding deadlock. So these toy problems could be looked at, or solutions to these toy problems could be looked at to understand the need for, or the use of, the synchronization or mutual exclusion primitives. and they are treated very nicely in many of the textbooks. Okay, now one additional concept which we are going to need later on, and I'll comment on that, what I mean by later on in a few minutes, is the concept of a thread. Therefore, I'd like to talk about the thread before wrapping up on concurrent programming. Now, we have talked about processes, and a thread is in some sense a related concept. We will think of a thread as being a thread of control in a process, hence the name thread. So in general, when I talked about a process, I talked about this worm squiggling through the process, which was a flow of control. Along the same lines, we now talk about a thread as being a thread of control within a process. And some people talk about a thread as being a special kind of process, but just lighter in weight. And I'll talk about that a little bit. Now, when people talk about the weight of a thread as related to the weight of a process, which is obviously what's happening in referring to a thread as a process which has light weight, they must be referring to something about the thread which is simpler or less expensive or less time consuming than the corresponding concept in the case of the process. And some aspects of threads which may be relevant in this context are that a thread is simpler than a process and therefore takes typically less time to create. A thread, as we're going to see, is simpler from a process in important ways through which it takes much less time to switch from one thread to another thread. And both of these are ramifications or symptoms of the fact that the size of the context or the size of the amount of information, data and operating system information or library information associated with the thread is much smaller than that associated with the process. So in order to understand what a thread is, we need to understand a little bit about what we mean by the size or the thread or the context of a thread. And just to go back to our understanding of what a process is, let me remind you something that we saw in connection with our discussion of a process as a data structure. This will help us to understand what we mean by size of context. Now, when I talked about the process as a data structure, we went through the exercise of listing the different operations that could be done on a process, and those ultimately were the different operations which were implemented as system calls. Subsequently, we started to look at the different pieces of data that were manipulated by those operations. And we came up with a large collection of different pieces of data that we viewed as being important as far as the process is concerned, and therefore the data associated with the process. There was a text data stack and heap, which was fairly obvious. There was the contents of the hardware registers associated with the process when it was running. And then there was a lot of operating system information which was associated with the process, such as identifiers, memory management information such as page tables, etc., various pieces of information. Now, all of this information is information that is associated with the process and could be described as the process context. In other words, the information that must be present or taken into account when that process is running. And we saw that when there's a context switch from one process to another, some of the information that is listed over here had to be loaded into the hardware context. And some of the other pieces of information had to be taken into account by the operating system, because whenever there was a system call during the running of a process, the operating system had to be aware which processes page table, which processes information about CPU time, which processes open files had to be referred to. Therefore, there was this notion that whenever there was a context switch, not only the hardware state, but the operating system perspective had to be changed to that of the incoming process. And the context of a process was fairly large. It filled one screen. Now, in saying that the context of or in saying that the time for context switch of a thread or the size of the context of a thread is going to be lighter than that of a process, the implication must be that the thread is some kind of an entity akin to a process, but with much less information associated with it. Therefore, it should be possible for us to list, for commonly occurring implementations of threads, what the information might be contained within the thread context. It turns out that this is typically quite small, so small that while it's obvious that each thread must have a unique identifier, just like each process had to have a unique identifier, it's obvious because if there are multiple threads corresponding to the execution of a program, then it may be necessary to switch from one to another, and that therefore they must clearly be distinguished from each other, for which reason each must have a unique identifier. If they are separate threads of control, separate flows of control in a program, then they would clearly be able to make function calls independently of each other, and must obviously therefore each have their own stack. Notice that I don't say each must have their own text or each must have their own heap. They could actually have shared text, data, and heap, but specifically must have separate stacks because they are threads of control and may make separate function calls. Clearly they must have separate stack pointers if they have separate stacks, and further they must have separate special purpose and general purpose context associated with them. If there are two threads and they are viewed as separate threads of control, executions inside the processor, and I can switch from one to the other, very clearly the meaning of R1, register 1 to one of the threads, is not going to always be the same as the value in R1 from the perspective of one of the other threads. Similarly, as independent threads of control or flows of control, they will be executing different instructions. Therefore, they must have separate hardware context of this kind, but that is pretty much it. So the thread context is going to be very small, possibly separate stacks and stack pointer and a few of the general purpose registers, the general purpose register file, as well as some of the special purpose registers. But other than that, threads need not have separate context from each other. In fact, as a consequence of this, the amount of time that is going to take to switch from one thread to another is going to be much smaller than the amount of time that it takes to switch from one process to another. This largely comes from the fact that the process context, which we listed on the previous slide, is so large. Now, the perspective that we could have is that we could have a problem in that we have to understand where the text, data, and heap associated with the thread are going to come from. It's well and good to say that the thread context includes only these things, but if a thread is an active entity which could run on a processor, then it must have instructions associated with it. And I haven't mentioned anything about its text or its data or its heap, which is why the next point is reassuring. The picture we should have in mind is that there could be many threads which are all part of the same process. In other words, they are all sharing many parts of the process context, such as maybe their text, their data, and their heap. So the picture we may have in mind then is that I could have a single process in which there could be many threads, and there is the common process context which includes text, data, heap, open files, etc. But each of the threads on its own may have a small amount of context of its own, and therefore when I switch from one thread to another, some of the process context between them could be shared. In particular, other than the stack, the virtual address space could be shared, as a consequence of which the threads T1, T2, T3 could actually have a large number of shared variables within the virtual memory framework of any operating system. Therefore, a lot of what we talked about in connection with concurrent programming could actually find implementation in the form of threads rather than implementation in the form of processes which are cooperating. Rather, we could think about threads within a process cooperating towards a common objective. The threads would have to be synchronized. The threads would have to have mutual exclusion on their access to shared variables. But those shared variables themselves could all be within a single process, and therefore not violating our understanding of the operating system's virtual memory in order to protect one process from another. This is a situation where the threads do not have to be protected by the operating system from each other. The threads, being part of the same program, would have been written to carefully and correctly utilize the shared variables in a manner that is good for their common objective. So much of what we have said may make sense in the context of the one processor machines that we run on, in the context of threads. Now, we therefore have this notion: threads running in the same process, having shared variables, but the stack allocated variables may not be shared for reason of the stack being part of the separate context of the individual threads. In other words, each thread has its own stack, and therefore its local variables and parameters are distinct from each other. Okay, now the question which will arise now is, we talked about processes before we talked about operating systems, and subsequently learned that the concept of process is created by the operating system. One of the operating system's jobs is the management of processes. The operating system schedules processes onto the CPU, etc. What is the status of threads? Are threads also operating system level entities? Now, there are actually two possibilities. it is possible that the threads could be implemented or supported directly by the operating system, but on the other hand, it is possible to have implementations of threads which are made available through a library. In other words, not implemented inside the operating system, but implemented outside the operating system through libraries of functions. And some of the systems that you deal with will have hardware operating system support for threads, and some of the others will not, in which case you would use a threading library in order to deal with threads. Now, one of the commonly available thread libraries is known as pthreads. Pthreads stands for POSIX Thread Library, and this is downloadable or available on many kinds of systems. What do you expect to find when you look at the thread library? What we understand by library is that it is a collection of functions and possibly associated data. So what kind of functions would we expect to find in connection with the pthreads or a threading library in general? Now, very clearly we'd expect that just like there's a system called to fork a new process, there must be some kind of a function inside the thread library to create a new thread. And in the case of pthreads, the name of that function is pthread_create. It returns an integer value. It takes various parameters. I won't go into the details of this, but this is reassuring because this would be the parallel of fork. It is how one creates a new thread. And there are various other functions included in the library for doing various operations on threads at the level of the process operations that we talked about. And I list some of them here, but will not go into the details. If it becomes necessary to use pthreads, one merely has to understand the library. Now, from our perspective, we've seen one function in the pthread library which relates to fork, but we have seen that when we talked about writing concurrent programs using processes, there was a need, the need for various synchronization and mutual exclusion primitives came up, and I suggested that the same requirements may exist if we are programming with threads, because threads do have shared variables. Threads may have to synchronize with each other, and therefore locks and semaphores may be important for concurrent programming using threads. So we would hope to see several functions available in a thread library for operations relating to locks and semaphores, and that is in fact the case. We find out that there are functions for doing operations on locks. For example, there is the pthread mutex lock function and the pthread mutex unlock, which serve the role of acquire lock and release lock in our earlier terminology. And as far as semaphores are concerned, there is a mechanism to initialize the semaphore on many systems, a mechanism to do the P and the V operations on semaphores. Whenever we see wait, we understand that that would correspond to the P operation, and post corresponds to the V operation, post or signal. Therefore, associated with these threading libraries, one does find support for the various issues that we saw in connection with concurrent programming. Now, I'm going to stop the discussion of concurrent programming with this. You may be wondering why I talked about concurrent programming in sort of a partial mode. For example, I talked about synchronization a little bit. I mentioned some other synchronization primitives but didn't go into them in detail at all. For example, I talked about lock and semaphore to some extent, but in an earlier lecture I had talked about something called the barrier, and I never said anything to you about that. You'll be wondering about this. You'll also be wondering about the relevance of this particular topic. Now, let me just warn you about things which are ahead. Later in this course, we're going to actually talk about some high-performance systems. Remember, the title of this course is High-Performance Computing. And many of the high-performance systems today, there is more than one processor. Up to now, our assumption has been that we are talking about computer systems in which there's only one processor, and hence only one process could be in execution at a time, or only one thread could be in execution at a time. What I mean by that is only one process could be running on the processor at a time, or only one thread could be running on the processor at a time, because there's only one processor, only one program counter, etc. But if in high-performance computing systems there is more than one processor, then there is a potential for a concurrent program to actually run with one process on one processor and one process on another processor. And if that is the case, then it's no longer fair to call it a concurrent program, because the activities on the two processors could actually be happening in parallel, in fact at the same time. So at exactly the instant in time when process P1 is running on processor 1, process P2 might be running on processor 2. And therefore, there is no problem of concurrency. There is actually a problem of events happening at the same time. And this might in fact be a more severe problem from the perspective of issues like mutual exclusion and synchronization than it was in the context of concurrent programming. Therefore, later in this course, when we talk about high performance computer systems with multiple processors, we will come back to many of these issues in more detail, which is why I am rushing through them a little bit right now. Now, coming back to our agenda, we are at a break point. We have successfully completed our discussion of process management, right? And we are about to move into the next topic, which is, as you will see, item number 5, labeled pipeline processors. And let me just switch to that material. So, we are now moving into the next topic, which is line item number 5. So, we have moved out of, if you're looking back, you will notice that for the last 10 lectures, we were on the software side of the computer systems. Prior to that, we were on the hardware side of computer systems briefly. We are now going back into the hardware side of computer systems for something like the next 9 lectures or so. We are going to start off with this discussion of pipelined processors. So, again, let me just remind you where we were when we stopped talking about hardware a while back. We are still in the context of thinking about a computer system in which there is only one processor. Our discussion of computer systems with more than one processor is several lectures down the road. And our understanding of the way the processor operates is that there is the need for the I/O devices and the memory, but we looked a little bit at the control and had a picture in which we understood the various steps which had to happen in executing an instruction. There was a need to fetch the instruction from memory. There was a need to decode the instruction. There was, in some instructions, a need to do a memory operation, and in some instructions, a need to do a write back. So we came up with simple hardware for each of the different steps in the execution of an instruction. And a question which we didn't ask at that point in time was, how fast can a processor be? You'll recall that when we talked about the implementation of a processor, we talked about how there was a general purpose register file. The correct operands had to be fetched from the file. For that, the correct operand may have to be fetched from memory. For that to happen, conceivably the address may have to be calculated and so on. But we never talked about the performance of the processor, which is the title of the current slide. Now, if we are to think about processors that are available today, we assume that they must be high performance processors, and that therefore their hardware is not going to be along the lines of what we have seen. They're going to have some ideas within them to improve the speed with which they execute instructions. Now, an important question in this context, which we need to understand to start things off, is what is the correct priority? Which is more important? Is it important to build the hardware so that it can execute each instruction in as little time as possible? In other words, is it important to reduce the execution time of a single instruction? Or is it more important to increase the throughput of instruction execution? In other words, increase the number of instructions which are executed per unit time. And if you think about it a little bit, these two are distinct objectives. If it was my objective to reduce the execution time of a single instruction, I would actually try to make I would try to optimize the piece of hardware for doing instruction fetch, instruction decode, etc., 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 and then put them all together to get the minimum possible amount of time for executing each instruction. We saw that for some instructions, the amount of time to execute the instruction was 3 cycles. For other instructions, the amount of time to execute the instruction was 4. For others, it was 5. And maybe by very careful design, I could reduce this to 2 and 3 and 4. And that would be what would happen if my objective was the first. The first objective would try to reduce the times by very, very aggressive design possibly. Whereas the objective in the second is saying, don't worry too much about the individual instruction execution time, but try to improve the rate at which instructions execute, which is an interesting concept. It's not too clear at this point how that could be done. But if you think about it a little bit, let's assume that our objective is to make our programs run as fast as possible. That's the ultimate bottom line. The manufacturer of a processor knows that the processor will sell well if it is able to execute programs faster than the competitors. Therefore, in some sense, whichever of these objectives will achieve that ultimate objective is probably the important one. And with a little bit of thought, one can actually argue and convince people that the throughput is where one is going to get faster program execution, not necessarily from the faster individual instruction execution time. Therefore, we are actually going to start looking at an idea in which the objective is, in fact, the second, trying to increase the rate at which instructions are executed, not paying too much attention to the amount of time that it takes to execute any one instruction. Right? In fact, not being too concerned if the amount of time to execute any one instruction is actually higher than it could have been. Rather, trying to increase the rate at which instructions are executed. Now, commonly used terminology for the rate at which instructions are executed is to talk about the number of cycles per instruction, and that's sometimes abbreviated as CPI, cycles per instruction. Right? And the general idea is that if I have a program which is going to execute, I can count the total number of clock cycles it takes to execute the whole program. I can also count the number of instructions that it took to execute the whole program, and then I can divide the total number of cycles divided by the total number of instructions and come up with the cycles per instruction number for the execution of a particular program on a particular piece of hardware. Now, for the kinds of design ideas that we've been looking at so far, you may ask, what would the cycles per instruction for a program be? And arguing along the lines that are suggested at the top, you'll remember that using the ideas that we have so far, where some instructions take 3 cycles, some instructions take 4 cycles, some instructions take 5 cycles, you'll notice that when I execute a program on a machine which has these characteristics, some of the instructions may take 5 cycles and some of them may take 3, but no instruction is going to take less than 3 cycles, no instruction is going to take more than 5 cycles. Therefore, however many instructions I execute, in other words, however many instructions have to be executed as part of running a program that I'm interested in, the CPI is going to end up somewhere between 3 and 5. It can't be less than 3, it can't be more than 5, it's going to be somewhere between 3 and 5, using the current ideas, under certain simplifying assumptions, of course. Now, we are going to look at an idea called pipelining, which is going to concentrate on the rate at which instructions are executed. It's not going to try to reduce the 3 to 2, reduce the 4 to 3, reduce the 5 to 4. The effect of doing that might have been to reduce the CPI to something like the range 2 to 4, and that's not very aggressive. What pipelining is going to try to do is going to try to reduce the CPI to something like 1, which is substantially better than the cycles per instruction that we were talking about for the ideas that we've seen so far. So it's a substantially new approach. Now, the basis of the idea of pipelining, in essence, from the context of the hardware that we have seen, is to try to get an answer to this question. In building the hardware that we had the hardware to fetch an instruction and increment the program counter, we had the hardware to decode an instruction and access the operands, then we had the hardware to execute the ALU, etc., the hardware related to the access to memory, if it is a load or store, etc. And then we just put these pieces of hardware one after the other and expected that it would be used to execute instructions. We never asked the question listed over here. The question is, after the piece of hardware which was meant to fetch the instructions from memory had fetched the current instruction, why do I keep it idle when that particular instruction is being decoded? Why can't I use that fetch hardware for something else? This is the fundamental question which answers to which provide the idea of pipelining. But before getting into the mechanics of pipelining, I'll just quickly suggest where the idea of pipelining may have been motivated from. Now, the suggestion from the name pipelining, you might guess that the motivation for the idea of pipelining came from petroleum pipelines. So, I'm just going to hypothesize why this may be a reasonable guess about where the inspiration for the word pipelining came from. Let me just talk a little bit about pipelines. I'm not a chemical engineer. Some of you may be and will have better ideas about pipelines than I have. Therefore, this is just a very general, rough kind of a perspective on pipelines. Now, pipelines are actually physical objects. They are used to transport fluids. The fluids could be liquids or gases over long distances. And when I talk about long distances, I could be talking about thousands of kilometers. For example, some of you may be aware about pipelines. For example, there's a well-known pipeline which stretches from somewhere near Mumbai in India to somewhere near Delhi, and that's thousands of kilometers. So these are substantially large distances, and they are used to transport fluids. Could be liquids or gases. And this sometimes arises in the context of transporting petroleum products from a refinery to a point from which they could be distributed. And what I mean by petroleum products, I'll elaborate on a little bit. But as far as the pipeline is concerned, one should have a picture of some kind of a pipe. I'm not sure what the diameter of these pipes would be. In some cases, the pipelines could be underground. In other cases, for cost reasons, they may be overground. But what's important is that they must have some periodic stations, periodic pieces of equipment, which could be used to pump or compress, depending on whether we're talking about liquids or gases. Because unless there's a pump to push the fluid through the pipeline, then the whole pipeline would have to have some kind of a gradient in order for the fluid to flow. And the objective here is transportation of the fluid, and therefore there may be a need for these pumps periodically. In addition to this, there may be the need for some protection mechanisms periodically, such as valves or things like that periodically. But in essence, the abstraction of the pipeline that I'll work with is something like this. There's a pipe, as we know it, running for potentially thousands of kilometers. And one example is it might be running from a refinery to a city. Now, a refinery is a place where petroleum is taken in, crude petroleum is taken in, and it is refined into many products. For example, it is cracked and one gets diesel, kerosene, airline fuel, etc. Various different kinds of things obtained from crude petroleum. And it's conceivable that all of them have to be transported to the city, to the other end. Now, one could actually think about, let's suppose that one can describe the amount, the volume of each of the different kinds of petroleum products that one has in terms of kilometers. And let's suppose that at some point in time I have the equivalent of 20 kilometers in terms of volume. The volume would be defined by the area of the pipe multiplied by the length that particular volume occupies if it's pumped through the system. So let's suppose that I have 20 kilometers of airline fuel which I want to transport from the refinery to the city. Then one thing that could be done is to just pump the 20 kilometers through the pipeline. Now, if that is the case, then much of the effort of using the pipeline is going to be spent in pumping air through the pipeline, because at any given point in time there's 20 kilometers. Now the 20 kilometers of airline fuel is here, and it slowly moves through the pipeline. At some point in time it's over here, and in pumping it you are basically pumping air in order to push the petroleum fraction that you have through the pipeline. So this is not a very effective use of the pipeline. A much more effective use of the pipeline might be that after having pumped the 20 kilometers of airline fuel, I conceivably have to leave a little bit of a gap, but I could then pump maybe 50 kilometers of some other fluid, maybe diesel, through the same pipeline. And after maybe a little bit of a gap, I could pump maybe 100 kilometers of some other fraction of petroleum. And in essence, by trying to keep the pipeline full, I'll be increasing the utilization of the pipeline. And in fact, I'll be reducing the amount of time that it takes for any one of these fractions to reach, if I look at the average amount of time across all of the fractions. In other words, here what we're trying to do is to improve the throughput of the pipeline. So this is an idea for petroleum pipelines of improving the throughput. And the key idea is, rather than just concentrating on one fraction, I concentrate on many fractions. I try to get many fractions into the pipeline so that the pipeline is full of many different fractions at the same time. Now, if we want to translate this into our processor context, I just have to replace the term petroleum by the term instructions and talk about this as being one instruction, this as potentially being another instruction, and so on. The general idea being that if I have a piece of hardware which is capable of executing instructions, then rather than trying to use all of the hardware for just one instruction at a time, in other words, that 20 kilometers of airline fuel, I try to actually use some of the hardware for airline fuel, one of the instructions, some of the other hardware for petroleum, for kerosene, in other words, one of the other instructions, and so on. In other words, try to use all of the hardware at any given point in time for various instructions so that none of the hardware is idle. And the net result will be that I might actually increase the throughput, in other words, the rate at which instructions are completed. So this seems like a reasonable guess as to where the motivation for pipelines came from. Now if I look at the hardware that I had for the processor, this is what it looked like. As I said, there was the hardware to do fetching of instructions and incrementing the program counter. There was the hardware to decode instructions and fetch the operands. There was the hardware to do various ALU related operations, whether they be in connection with arithmetic instructions or load store instructions or branch instructions. In all these cases, the ALU may have to have been involved. And then there was the hardware to do operations on updating or reading from memory, such as load and store instructions. And up to now, our picture was that we can just use all of this for one instruction at a time. I had, at the time that we went through this description, I had introduced a label for each of the now 5 steps in instruction execution. The labels were IF, ID, EX, MEM, and WB, standing for instruction fetch, instruction decode, instruction execution, memory access, and write back. Now in the lectures to follow, I don't want to repeatedly reproduce this detailed diagram. We in fact don't have to look at the details of the individual components of the hardware too often, and therefore I'll try to use some kind of an abbreviated notation, which may in fact just look something like this. Rather than drawing the instruction fetch hardware, I may just draw a yellow block and label it IF for instruction fetch. Similarly, for instruction decode, a gray block labeled ID, instead of this instruction execute, a red block labeled EX, and so on. So I will use this abbreviated form, and when in doubt, in some situations I may refer back to the full diagram, but typically the abbreviated form will suffice. Okay, so the fundamental idea of pipelining is that we are interested in trying to maximize the rate at which instructions are executed. So we will keep steady track of time. Now when I draw this timeline, just to make sure that there's no confusion about our recent use of timeline. Our recent use of timeline involved either process virtual time or it involved real time. In this particular context, we are back to the hardware level, and therefore we're talking about the hardware timeline, which is more akin to the real timeline, but in which we are actually concerned about the individual cycles that are going by as the activities proceed. So if I consider, and I could therefore label that timeline as clock cycles, and in fact, since I know that the clock cycles discretize the timeline, I could henceforth view the timeline as being this discrete version, where there is the first clock cycle, which is the time between here and here. This is followed by the second clock cycle, and so on. So from now on, we'll actually have a discretized version of the timeline: clock cycle 1, clock cycle 2, etc. And in most cases, we will not be too concerned about the various activities that happened within clock cycle 1, for example. In some cases, we may have to, but not that important for the moment. So what happens as instructions execute? Now our current picture is that the first instruction executes will execute by spending one clock cycle being fetched, one clock cycle being decoded, one clock cycle being executed, etc., etc. If it's let's say an instruction which requires all the 5 aspects of the hardware. What about the second instruction in execution? Now our current assumption is that the second instruction will start executing when the first instruction finishes execution. In other words, it will actually use the IF hardware in the 6th cycle. It will use the ID hardware in the 2nd cycle. I'm referring to the second instruction, and so on. So based on our current understanding, the second instruction would finish execution in the cycle numbered 10. Right? It would finish right back in the cycle numbered 10. But just based on the question that was just asked, the question which was asked in the slide before last was, after the first instruction has used the IF or the instruction fetch hardware, why do I keep it idle? Why is the instruction fetch hardware kept idle for 4 cycles? Why can't I use the instruction fetch hardware to fetch the second instruction right away? In other words, why not fetch the second instruction in cycle number 2 rather than waiting until cycle number 6 to fetch the second instruction, and so on. So the second instruction can be fetched in cycle number 2, it can be decoded in cycle number 3, it can be executed in cycle number 4, you can use the MEM hardware in cycle number 5, and it can be written back in cycle number 6, rather than actually finishing only in cycle number 10. So this is in essence what processor pipelining will try to do. So note that as far as processor pipelining is concerned, the fact that each instruction took 5 cycles is hardly a concern at all, because what we have achieved is more important. So the third instruction can follow and use the IF hardware starting from cycle number 3 and so on. What is the net effect? The net effect is that just like in our previous simple perspective of the hardware, the amount of time that it takes to execute a single instruction is still 5 cycles. But with this new perspective on reusing the hardware as soon as possible, the rate at which instructions can complete is now 1 instruction per cycle. And how do we see this? We see this if we look at the time that instruction 1 completes. Instruction 1 completes in cycle 5, instruction 2 completes in cycle 6, instruction 3 completes in cycle 7, and so on. In other words, even though it takes 5 cycles for any one instruction to execute, every cycle an instruction seems to be completing in this diagram, and therefore the throughput or the rate at which instructions execute is 1 instruction per cycle or 1 cycle per instruction using our CPI notation. Okay. Now the one thing I would want to point out from the perspective of the diagram, since the diagram is up on the screen, is that it is true that an instruction is completing every cycle starting with cycle number 5. In cycle number 5 instruction 1 completes, in cycle number 6 instruction 2 completes, and so on. But if I look at the first 4 cycles, no instruction completed. Therefore I do have to note that there was this initial time of 4 cycles during which the pipeline was filling up when no instruction completed, but after that the throughput of this pipeline is 1 instruction per cycle. And therefore this simple idea, if it can be implemented, is very successfully increasing the rate at which instructions are completing, and can therefore successfully reduce the amount of time that it takes to execute a program. Now we will look into the details of pipelining and the problems that arise in the design of the hardware to achieve the objectives of pipelining in the lectures that follow. I will stop today by just reminding you that we have now, in this lecture, we have begun the transition from the software side of computer organization back to the hardware side of computer organization. We are now going to look in a little bit more detail at one of the more recent developments in computer hardware where pipelining is used. This is in fact a development which happened more than 20 years ago, but the earlier ideas that we had seen predated even that. So this is an important stepping stone for us to understand the nature of processors today, because on the processors of today we can definitely expect that pipelining is a widely used hardware phenomenon, and that's something which as programmers we may well have to be aware of. Thank you.